Yes, thank you, UN, and thank you, Boutaina, for the very comprehensive representation of the work done so far, and for introducing the tools I will build upon to present the results of the work package dedicated to studying the impacts of the climate change on the structure design. So it's a joint work with several colleagues, especially Colleen and Tessa from France Énergie Marine. We are working in this project. So if we go on to the objectives of this work package, well, as introduced by Boutaina, the one of the objectives is to compare the numerical wave and water level reanalysis on the French seafronts in order to select the one that is well in accordance with the observations. Then we proceeded with statistical downscaling of waves and water levels, and which allows to study the impact, to assess the impact of climate change on waves and water level for application to the design of offshore wind structures. So the first of all is to study the extremes, how the extremes are changing with time. What are the impacts on the operations and maintenance, and what are the impacts on the landing zone and on the fatigue. So if we go on to the first task of selecting the databases, we have two main components here in addition to the wind. So the first one concerns the waves, which impacts the structures. So we used in situ data from the Copernicus in situ TAC, and we selected the buoys that are located within our zone of interest, and also that have sufficient data in terms of coverage and missing values. So we ended up with 12 buoys located in the English Channel, the Atlantic coast, and the Mediterranean Sea. And we wanted to compare this data to reanalysis available. So we compared for the Atlantic and the English Channel two reanalyses. So the first one is resource code, that is from Ifremer. And the second one, which was done by the SHOM, which is called IWAT, which are two recent reanalyses available in these areas. And for the Mediterranean coast, we used the MEDUG, which is also from the SHOM, and the MedWave database that is from Copernicus. And concerning the water levels, we worked with the Ronin network from the SHOM, which is the tide gauge stations. And you have 23 tide gauge, 7 in the Channel, 11 in the Atlantic coast, and 7 in the Mediterranean Sea. And for the reanalysis, we used the GTSM database, which is forced by ERA5 and available on the Copernicus Climate Change Service, and EBMFC, which is developed by Copernicus. And for the Mediterranean coast, we used the GTSM, which is the same as above, and the MEDMFC, which is also provided by Copernicus. So the idea was to select the one that is the best suited, the reanalysis that is corresponds the best to the observations. And to do so, we compared, we used several tools, and I present here an example of what we have done. It's called a Taylor diagram. On the right of the slide, it allows to compare several characteristics of the databases and to compare different models. So here it is for the English Channel. So you can compare the angle, will compare the correlations between the observation and the model, and the radius will correspond to the standard deviation. So the closer you are to the reference, the better you are. And studying such kind of graphics for the different locations that have been presented by Boutaina, so the representative points. We've selected to IWAT in the English Channel and the Atlantic Ocean, and the results on the Mediterranean Sea will be based on the MEDWAV project from the SHOM. And for the water levels, we used the GTSM reanalysis, which provided the best results in accordance to the Ronan network, the data we've attained. So once we have selected the reanalysis, we have to use climate models as presented by Budaina. So here we did not run GCM. We have to base our work on data already available. And for waves, it is less numerous as for the wind. So we use for waves a recent work from Mercy that ran the numerical wave model, which is a WaveWatch, on a global configuration forced by different wind models that are presented here on the left table and are available for the period we studied. And then for the surges, it's another kind of numerical model, which are forced again by the GCM, and we have 5 here models, GCMs that have been used to force the model. And for these cases, if you go on to the next slide, Yuan, please. We have several periods that are covered. So the historical period for the waves will correspond to 1985 to 2014. And we have 2 different scenarios, so the SSP1 2.6 and the SSP5 8.5 that are available with a gap in the data. It begins in 1971 to 200 and 2100. And for the surges, we have an historical period that is much longer, and but we have already only one scenario, the SSP5 8.5 from 1915 to 2050. So the early late period. So if we now compare, as it has been done, presented by Budaina, we can compare 7 characteristics here. I will start with the mean wave height evolution before going on to the extremes. So if we look at the way the mean significant wave height is changing, well, we have a good accordance between the different models that are represented here by the box plots, and a good agreement between the model that we have a lower mean significant wave height at all the locations we are studying here, which is especially true for the SSP5 8.5. So, and we have a decrease in the median in all the locations. And here I do not show, but we also take a look at the seasonal evolutions, and the results are not very clear. And we also observed very small evolutions of the peak period TP, which is not shown here, but it's also carried out during the project. If we go on to the next slide concerning the I quantiles of the significant wave height, the quantile 95%, we observe a negative trend in the Mediterranean Sea, a positive trend in the Channel, and quite difficult results to see in the Atlantic with a more mixed signal. And the next message is that the most severe scenario, the SSP5 8.5, amplifies the trends explained earlier. But as seen for the winds, there is a very large model spread, meaning that the changes are very different from one model to another, meaning that the climate signal is not that clear. If we go on to the next slide, Ewan, so for the first 2 slides were about waves, and now we want to study also the mean sea level, which is known to be rising due to the different effects. Here we have one model from LeBars, and only one scenario, which was taken from the RCP 8.5 scenario of the IPCC at 1 degree of resolution. It is this sea level that forced the climate projections. And what we observe is that we have a similar increase over each representative point, and a slightly lower increase for the east channel, but the impact of the mean sea level on the total water level is very important, since it is very clearly increasing variable. And if you go on to the next slide, UN, we studied, in addition to the mean sea level, we also studied the way the negative and the positive surges change with time. So the surges were identified using, it's an output from the model. It is the effect of the atmospheric effect on the water level, having removed the effect of the mean sea level and the tides. So it is only the atmospheric part of the water 8. And both components are interesting for these structures, both the negative and the positive surges. And what we have here, it is that we have an augmentation of the mean sea level as represented on the table for all the locations. Here you can see that there is a clear positive trend in the mean sea level. And for the negative surges, it is a high confidence in having a lower negative and positive surges with a high agreement level, but kind of a variable significance level depending on the models and depending on the representative points. We observe only a negative absolute change between the baseline and the near midterm, which is the end of the database available here. And we have to take care that it represents less than 1 centimeter. So as said before, the mean sea level increase is more important than the past changes in surges. And once we have kind of detailed what was the changes observed, here we also want to carry out a more study specific to the extreme, which is the goal here of the next slide. We will do it for wind, for waves, and for water levels, for surges. So what we have done is we computed the 50-year return level from a non-stationary model, a non-stationary GeV model specific to the monthly maxima, and we computed back the 50-year return level, which allows to see how the very extremes, the more extreme extremes, are evolving, and we base our study on the statistical results of using the GeV model. So what we see is that all regions show an increase in the extreme values under the future climate scenarios. So here we represented in two figures the evolution of the return level, the relative changes from two scenarios. So on the left you have the SSP1 2.6, and on the right you have the SSP5 8.5, and we compare the estimates of the return level depending on different models, which are the points of the box plots, and we represent also the spread between the models with the mustache with the box plot. And so we see that at nearly all the locations we have an increase in the extreme values, with higher changes in the West Mediterranean, and that's the consistency is quite good, especially for the Atlantic, which are very consistent projection in the in an increase of the return levels, which is important from a design perspective. And also we can notice that the higher emission scenario leads to higher extreme values. And we have also a large model spread, especially in the Mediterranean Sea. So this is the result for waves. If we go to the next slide, to storm surges, You have the negative storm surge on the left and the positive storm surge on the right. And we see that we have the largest projected increase in the East Channel, which is the region that shows the much more important changes. All the variables are increasing. So both the negative surge and the positive surge are increasing, meaning that the negative surge is increasing in absolute value. So the low value are becoming more low, and the high values are becoming more extremes, which is an augmentation of the variance of the phenomena that is a known consequence also of climate change. And here again, we have a kind of a large model spread. But the changes are not shown here because I only show here the relative changes, but the change are of the same magnitude as the rise of the mean sea level. So it is the same order of magnitude. So it's a change that may be important for the design of structures. And on this topic, the next slide will be the last about the extremes analysis. It is the result for wind speed, 10 meter wind speed. Here we do not see a clear consensus between the models. It seems to have a consistent increase from the baseline to from midterm to long term above each region. But here the changes are very induced by the spread of the model, and here our uncertainty kind of dominates over the climate signal. So it's kind of difficult to come up with a clear picture of what is happening here. So it's less clear for wind speed that the extremes are going to change. So if you go on to the next slide, UN, we also in this work package studied the impact of operation and maintenance. So we have two slides here. So the first one concerns the weather window. So it is just a count. There's no model behind here. We just count the number of weather window defined by a simple criteria, which is a significant wave height to be less than 1.5 meter and we compute this number for each month and we take the averages. So if we look at these pictures, there are no big differences between them. The most important differences are in the Atlantic, both North and South Atlantic representative point, where we see that in late summer, the SSP5 8.5 shows a clear increase of the number of weather windows that are below the threshold, meaning that we will observe a longer period of time late summer with a significant wave height lower than 1.5 meter, which is a range of about 100 windows more in the summer. But again, here it's maybe difficult to see, but we have a large model spread, and the uncertainties between these figures are quite large. And the next slide will not concern the weather window from HS, but if you go, yes, thank you. It concerns the weather downtime. It is the consecutive, the time we have to wait before you can operate, for example. So it is the time, the waiting time in days for between two consecutive time where the wind speed is lower than 5 meters per second. And what we see here, it is the most important change. It is in the East Channel at the first representative point selected. And we have 2 days more in weather downtime in December and January between the long-term scenario and the historical baseline period. And again, we have a large model spread. That being said, we will present also two results on the impact on the landing zone here and on the fatigue. It is a work carried out at the ENPC by Marissa Yates with Olivier Cadou from FEM and Nicolas. I will try not to tell something wrong about it. So the idea is that the electricity produced as the offshore wind farm will be carried to the coast using a cable buried in near shore to be protected from hazards. And this cable is subject to risks. So the first one is the erosion risks, which may lead to free spanning and mechanical failure, or accretion on the cable, which may cause overheating and again failure or reduced functioning. So the objective within the project is to define the state of the art to take into account the morphological evolution of the landfall, considering the climate change impacts. So the work is based on the hydrodynamic and morphological data at the landfall. We selected the wave and water level scenarios based on future climate. And two processes were proposed, either a process-based model to model the short-term evolution, or a reduced complexity model to present the slow evolution, long-term evolution, and then to combine the results to determine the straight line. So if you go into the results, UN, we have the year results that has been done at Portsmouth Beach, which is a beach not far from where we are located at Ifremer, which is an advantage of having high quality and high frequency data to calibrate the models. And we can see on the left-hand side the evolution to from medium to long-term evolution. It is the way the mean profile here, it is the dashed line, changes depending on different parameters of the model. So depending on the sediment thickness, with the evolution with the climate change. And on the right-hand side, we see a more storm-based evolution, which is evolution of the profile of the beach from events selected in a future climate from the different models we have at end here, and the most severe extremes that have been selected based on the extreme modeling approach to study the impact of specific storms in the future. So this work leads to a report that is presented on the right. It is part of the output of the project. And there is still important perspectives for future work. So to evaluate the uncertainties, to use continuous wave projection for long-term assessment. There is also the need for sensitivity analysis to calibrate the model, and maybe using satellite observation to improve the access to morphological observations. So if you go on to the next slide, it is the last work carried out in this section. It concerns the impact and design for fatigue, which is a work that's been done by INOCI with Clémentine Girandier, Matteo Pilmou, and Thomas Podentier. So the first task was to select the data. So it is not realistic to run the complex numerical model for all the possible situations. So they selected only a few subsets of possible both past and future sea state conditions to run an aerial elastic simulation on these selected locations to numerical design of experiment to select this location, and then this database is interpolated from the future time series to compute very quickly the damage equivalent loads for the different conditions. And then these conditions are weighted according to the past and to the future climate. So it has been done using a 10 megawatt IEA wind turbine with monopile foundation using an open source OpenFast software. So if you go into the results on the next slide, UN, I present here the results only at two locations, two representative locations, Saint-Brieuc and Saint-Nazaire. So we see for different models how the damage equivalent change. So the two moments at the tower base, the X moment and the Y moment, how this fatigue changes with climate change, which is a complex interaction of the mean and extreme fatigue. So on average, what is important to see is that there is a global decrease of the DEL across the climate scenarios. We also observe a high variability among models and sites, which is not shown here, but there is a high variability. And the potential impacts are important because it may lead to an increase of the operational lifetime of offshore wind farm, or for compensation of other adverse consequences, such as more frequent extreme events. And here we studied only wind speed, significant wave height, and the peak period of wave, but we neglected the other potential driving factors, such as the turbulence, the wind shear, the sea level rise, and the wind wave direction, which has to left for future work. So I just have one slide left concerning the takeaway messages of this world package. So in general, we have a decrease in mean conditions for HS and storm surges, but an increase of extreme events for HS and storm surges with rather unclear results for wind. But these two facts leads to globally decrease in fatigue on average across the different models. And then the more important changes, either decreasing or increasing, occurs for the most extreme emission scenario. And what is important to notice is that we have a large model spread, which means that we do need to use the different models because it gives a very important information about the spread and different possible future. So the limitations here, as said before, concerns the number of models used and the temporal resolution used. And also the number of models is important, and the downscaling approach to treat the extremes also is important and will be studied in future work. So we have to quantify the different sources, the model sources, and the statistical uncertainty that's been done during the project, but there are still some improvement to do. And also for the different impacts, we need multivariate modeling of extremes, which is also leads to the path to future work.